So we'll have two 20-minute talks. After the first talk, we will have a 20-minute intermission. I'll come back, put on my other hat, along with Danny Krolikowski. We will do the news. And then we will have our second talk of the night. What else? As you can hear right now, there's a train. There will be many more trains. We are next to a train track. That's what they do. So when a train comes by and you can't hear the speaker, we ask you to raise your glass and say, choo-choo. Choo-choo. Thank you very much. And we have our lovely merch table. Come check out our merch. We are claiming that we have new merch. I don't know what's there. You can check that out for yourself. Unfortunately, there will be, there's temporarily no live stream right now. That doesn't matter to you because you're here, but if you wanted to watch online, you can't. So we'll try to figure that out. And please tip your lovely bartenders. They are here for you, and we hope you enjoy the show. So without further ado, we will have our first speaker come on up. Take it away.
Thank you. So today I'm going to talk about the universe. Has anyone here heard that the universe is expanding? Anyone? Oh wow, we have a very large, like a very knowledgeable crowd here, so I can't say everything that I wanted to say. But let's first make sure that we are on the same page. So if
Sorry, working on it.
Okay.
I swear it worked 5 minutes ago. There we go. Okay, test the clicker out. Perfect.
All right, so let me just briefly explain what I mean by the expanding universe. So by this point, we already know that our universe has to start somewhere, some time ago. So what people believe right now is that the universe came from a Big Bang, that at the very beginning there was a Big Bang event, that the universe went through a very rapid expansion in a very short amount of time. And this phase is known as the inflation. And after this very rapid expansion, the universe expansion was expected to slow down over time because of gravity between matter. So anyway, we knew that the universe was supposed to be expanding for quite a little bit, but eventually we expected the expansion would stop, and at some point it might even reverse. It might even start to shrink, creating something called the big crunch of the universe. But then when people were finally able to measure the actual expansion of the universe, what they found was that the expansion was not slowing down. In fact, the expansion was accelerating, especially in the past 2 or 3 billions of years. Has anyone here heard about the accelerated expansion of the universe? Oh wow, very good. So in this kind of new universe history, we still think that the universe came from a Big Bang, that at the very beginning, the universe went through very rapid expansion at the very beginning, a very short amount of time. And then the universe continued to expand a little bit, slowly. And then at some point in the past 2 or 3 billion years, the universe expansion all of a sudden started to accelerate. Like everything just gets blown apart again. So this kind of accelerated expansion history was discovered about 30 years ago by observations of type 1a supernovae. So type 1a supernovae refers to exploding stars. They are very bright in the sky, so astronomers are able to find them even when they are very, very far away from us. And we were able to determine the distances to these exploding stars. And we also happen to know when the explosion happens. So when you start to put the time that the explosion happens, which is indicated on the x-axis of this plot here. And if you put together the distances to these exploding stars, something unexpected happened. So before, when we didn't know the universe was expansion was accelerating, we expected that the distances of these exploding stars would somehow lie along the blue line, because there are some distances to these stars. But instead, what they found was that the distances of those exploding stars was further away than what we expected. So if you look at some exploding stars here, maybe around like 1 billion years ago, we expected them to be here on the blue line, but somehow they were further away from us by a few percent. So this could only happen if the universe expansion was faster than what we expected, that there was more space between these very far away stars than what we previously had expected. So this discovery was made about 30 years ago, and was soon verified by a couple of different other observations, including galaxies or cosmic microwave background. So it became a very well-established fact that the universe expansion was accelerating to the degree that it was awarded the Nobel Prize in Physics about 20 years later. So it was a really big deal. The universe expansion, accelerated expansion, is pretty weird, but we also need an explanation. So here I'm listing several of the explanations I've heard people talking about. The first explanation is that general relativity is wrong, also known as Einstein is wrong. So I guess people just got into a habit of blaming Einstein for everything. Is there anyone here that believes in that explanation? Oh, wow. Are you waving because you believe Einstein is wrong? Yeah, sorry. I thought that there might be someone thinking the same way with me. So although this explanation is not my favorite explanation, it is actually a viable explanation. And there are still many scientists actively studying this scenario even today. They try to modify general relativity in ways that explain everything, every physics we already know, but somehow can also explain the accelerated expansion of the universe. So it is still being actively studied. But the second explanation is more popular than the first explanation, which is something called dark energy. This basically says that our space, our universe, is filled with a kind of energy that is completely invisible to us. Therefore, it is called dark energy. So this concept of dark energy, when I first heard about it when I was a first-year graduate student, I thought it was a concept from the Star Wars. But it turned out that it was a pretty serious theory, and it was a pretty elegant one. So later, I'm gonna hope that I can convince you that this is a really good theory and it's a really elegant one. And then finally, the third explanation I've heard people asking me about is dark matter, which basically says that the universe is filled with this mysterious form of matter that is also invisible to us, called dark matter. So unfortunately, dark matter does not explain the accelerated expansion of the universe, but it is a very important component of the explanation. So I'm going to spend some time explaining dark matter. When dark matter was first discovered or proposed, it was a very strange concept that somehow there was these things in our universe that we just couldn't see it in every possible way. But the mechanism that people use to discover dark matter is pretty straightforward, and there's just little disputes that it is true that they exist. This mechanism is based on the fact that things tend to orbit around a big body of mass. For example, our Earth is a big body of mass. Therefore, it attracts all of these satellites and the moon to orbit around the Earth. So this is all of the orbits of the things around the Earth is pretty well determined by the mass of our Earth. So if you look at a satellite, for example, the International Space Station, you can calculate the velocity and what orbit the International Space Station stays on pretty well. And the International Space Station orbits around the Earth pretty fast, like 90 minutes every round. Has anyone here tried to see the International Space Station? Tried to watch it? Oh, wow. 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 So to be honest, I've tried, but I've never been able to see it because my friends said that I just was not fast enough. Like you have to just really stare at the same spot. So I'm still hoping to see it one day. But for those of you that have seen it, would you see that the International Space Station moves pretty fast in the sky? Okay. I see some nodding hands ahead, so thank you. Yes, so the International Space Station moves pretty fast around the Earth because it has a very low orbit. It's close, pretty close to the Earth's surface. But when you go further away from the Earth, then the speed of objects starts to slow down. If you look at like those geostationary satellites, their speed would have slowed down quite a bit compared to International Space Station, and then they are able to stay relatively stationary to the surface of the Earth. And then even further away, you have the moon. And I guess everybody here has seen the moon before, right? No? Really? Have you not seen the moon? You should check it out one day. It moves very slowly in the sky, and you can see it pretty well. Basically, the trend here is that when you have a big mass, body of mass like the Earth, the further away you are from the Earth, the lower your speed is. It decreases. So the same mechanism can be used to measure the mass of a galaxy. So the galaxy has many stars rotating around the centers. So if you measure the speed of the stars rotating around the center of the galaxies, you could decide the mass that lives in a galaxy. This is very similar to the Earth. So at the beginning, when people started measuring it, we expected that the speed of all of the stars rotating around a galaxy would drop as when they get further away from the galaxy's center. Oops. Like the red curve here, but that turned out not to be true. Instead, they say that the speed of the stars rotating around the galaxies tends to stay flat, which means that there's a lot of extra mass that was somehow out there at a very large distance from the galaxies. So this phenomenon was first discovered by a scientist at Caltech. His name is Fritz Zwicky. He proposed that because of all of the extra mass that was indicated by the rotational speed, there must be a lot of invisible mass, dark matter there somehow. And that was in the 1930s, so nobody believed him. And then 40 years later, another astronomer, Vera Rubin, measured it again, but with much better evidence. And nobody believed her for a while. And eventually everybody starts to see the same thing around all of the galaxies. So eventually, that becomes the fact that there just has to be some extra mass out there in the universe in almost every single galaxy. So according to these measurements, almost over 80% of all of the matter in the universe is not visible to us and has not been anyways. It is known as the dark matter. And everything that we know visible to us, like human beings, buildings, bears, and the air we breathe, that is all visible matter that we know and we can touch, we can feel. So there's all of those things out there known as dark matter. But to physicists, dark matter and visible matter are pretty similar because they mainly interact gravitationally. So when you have a big piece of chocolate cake somewhere out there, and when you have another piece of chocolate cake, these things always produce a little bit of gravitational force on each other. And gravitational force is always attractive. So that means these things are always attracting each other closer and closer. So in a universe, this means whenever you have a galaxy somewhere, and if you have another galaxy somewhere, and if they have a lot of matter inside them, you know, visible matter, dark matter, and you have another galaxy with visible matter and dark matter, they're always attracting each other through the gravitational force. So if you give these galaxies enough time, they would eventually just come together, they slowly progress towards each other, and they would form big parties of galaxies. And this is also why we expected that the expansion of the universe to slow down, because everything wants to come together because of the gravitational force. So dark matter in that way does not explain the expansion of the universe. So then there has to be another explanation. So physicists' explanation to this is that there is a lot of energy in the space. When I'm feeling particularly dark on some days, I just explain to people that energy is like explosions in space. So if you have some galaxies, chocolate cakes that somehow wants to come together and form a bigger chocolate cake, and if you put an explosion between them, then they get blown apart a little bit. So that is the effect of energy, that they pushes things apart. Now if you look at galaxies in this kind of picture again, so we have one galaxy here and another galaxy here. Because of gravity, they always want to come together. And then there is the energy in the middle that is slowly blowing them apart. So if it's purely gravity, we eventually would have everything, all of the galaxies coming together. But if it's purely just energy in the space between them, then everything will be separated. So energy and gravity in the universe would have an opposite effect. They are kind of like a tug of war. One is counteracting the effect of the other. Now another thing that people really like the concept of dark energy is that dark energy in the universe changes over time differently from matter. So let's talk about matter again. So at the beginning of the universe, a lot of matter was created, and then the universe expands. So this also means that the matter, as the universe expands, as the space expands, matter will be gradually thinned out over time. So matter's density has been dropping, like just because the universe has been expanding a little bit. Now energy is associated with space. So whenever you have space, you just have energy. And the energy density stays constant no matter how much the universe expands. So this means that at the beginning of the universe, your matter is very dense. Your matter and the gravity it has is having a lot of effect. It's having very strong effect on the universe expansion history. But then slowly over time, matter thins out, and energy, becomes a dominating force there because it starts to override the effect of matter. So by the way, the x-axis, you can think of this as time, and this is the very early phase of the universe, and this is where we are now, and this is the future of the universe. So matter's density gradually drops and energy stays constant. So at the current day of the universe, we think that energy is already a dominating force. That if you look at all of the GeVs, which is another kind of calculation of energies that's associated with dark energy and matter, dark energy now makes up about 70% of the universe. So it is a dominating force of the universe right now. This also means that when you look back at the history, expansion history of the universe, then you now understand why the force of the acceleration of the universe expansion has only started in the past 2 to 3 billion years. At the beginning, we still have the Big Bang, very rapid inflation, but matter was still pretty dense there, so matter with its gravity effect is slowly slowing the expansion down. So expansion was slowing. And then when the matter was stretched thin enough, you have dark energy, and it starts to push things apart. And all of the accelerations there starts to appear, and it will only get worse over time. So by just adding one single term in the physics models, the energy term in our universe models, people are able to explain this pretty complicated expansion history of the universe, which makes it one of the favorite explanations for the whole universe history now. Now that said, there are still many things about dark energy that we don't know of. So, we really don't know what kind of energy it even is. We just think that it has to be energy. So there are still many ongoing cosmological and astrophysical programs that are trying to understand the concept of dark energy. One of the programs here is DESI, which is located at Peak Observatory, local to Tucson. This is one of my favorite experiments, and I also happen to be working on it. So if you are interested in seeing DESI, and if you have time and you are lucky enough to have a ticket, you could even get a public tour of the DESI at the Cape Peak Observatory. Another experiment that I program that is exploring dark energy, which is also my favorite, is the Legacy Survey of Space and Time. So this is located at La Serena, Chile. It uses a larger telescope than the one in Tucson, but you have to travel further to see it. So LSST, it is still being actively built, but you probably will hear news about it in the next couple of years. Now just wanted to mention one more thing about DESI, the experiment hosted by Tucson here. So DESI's main mission is to map the spatial distribution of millions of galaxies that are around us. And then they look at the spatial distribution of those galaxies and the small features in them to map out the whole expansion history of the universe. In the past couple of years, DESI released the first result from its first batch of data. And it found a tantalizing hint that the dark energy might not actually be a constant energy. So it might not even be an energy in the end. I see this is a tantalizing hint because people really are not very confident that what they are saying there is true. There is still, quite a significant chance that this just turns out to be some errors or noises in the data. But I think in the next couple of years, things are gonna get really exciting, and maybe we would have some definite answers on this kind of dark energy properties there. So that's the end of what I have to talk about. I'm happy to answer any questions.
Thank you so much for that very fascinating talk. Oh, don't go anywhere. I'm going to answer some questions. The audience has burning questions, and we have time for a bunch of them because you talked so fast. So that was great. Any questions?
The new telescope, the name I can't think of, the NASA director. Are they using the new space telescope for any measurement? Something like that.
Are they using the new NASA Space Telescope for any measurements of dark energy?
So I think you might be talking about James Webb Telescope, JWST. It depends on whom you ask. So there are some possibilities that it could tell us about dark energy, but it's really not its main purposes. So in order to study dark energy, people usually need to measure a lot of data, and JWST is better at studying a very small number of objects. So there's some chance that we could get some answers from JWST, but it's really not its main purpose, I believe.
Is the atmosphere around it like that?
So the question is, does observing from Earth rather than from space makes it harder to figure out dark energy, right? So the answer is, I believe, from my personal view, is yes. I always prefer space telescopes whenever it's possible, but they are much more expensive to build and much harder to operate. We do have another space telescope going up in the next couple of years. I think it's called Nancy Grace Roman Space Telescope, going up in 2026. And one of the main missions is also to study dark energy, and it can study many more galaxies than JWST. So dark energy is one of its main missions. So the question is, if dark energy is not a constant, what are the dependencies it has on properties? So if it's not a constant, we expect that its densities to change over time. That also means it's not a constant. So I'm not sure it answers your question. But to be honest, we don't really have a lot of explanations for dark energy. There are some theoretical explanations, but so far they all seem to be pretty off from what we know about dark energy. So I think our best guess is just to measure how dark energy changes over time and wait for a theory to pop up somewhere from some smart person that explains everything. So this tantalizing hint is from the year 1 analysis of DESI. So you're asking how many years do we still have left of DESI and how much we expect DESI to improve. So I'm not an expert on that. I think DESI is already thinking of extending its mission, so I'm not sure what the number is right now, but I think it's expected to operate for about 5 to 10 years. In terms of improvements, naively I would expect 2 to 3 times improvement, but there's also a lot of other factors that they combine with data from other experiments there, so it might not be improving there. So not sure that yet.
Okay, let's thank our speaker one more time. Okay, we will take an intermission for 20 minutes, so we'll be back here at 8:20 for the Astronomy Comedy Hour with yours truly, and then we will have our second speaker of the night. Yeah, go get drinks and come out and check out our merch table. Thanks. Okay, welcome back everyone. I'm taking off my MC hat. I'm putting on another silly hat. It's time for Astronomy in the News with me, Jackie, and with Danny. So we're going to learn some things today about the current events in astronomy, and Danny's going to start us off.
So we, this table is, well, whatever. So we start tonight's news program with a special alert from the Astronomy in the News weather team. The sun is big mad. So we're a little maybe late for a special alert on this, although I think this might need to be a recurring segment for the next couple of years with how things are going. But you may have heard kind of some hubbub over the last few weeks about the sun, which is in a bit of a mood. And why is it in a mood? So it's unleashing a lot of pretty crazy solar weather, a lot of winds and flares that are impacting not just the sun, but the Earth and all of the other planets. And so what's going on? So the sun is entering currently what's known as solar maximum. And so this is the point in the solar magnetic cycle where the sun is at its most active. So over the course of about 11 years, the sun goes through a cycle where its magnetic field is pretty weak, and then over time it gets stronger and stronger, it gets all twisted up. The points at where the magnetic field is strongest and twisted create sunspots, so dark spots on the surface of the sun. From those spots, the sun will flare, extreme radiation will be thrown off, its corona will explode and throw off highly energetic charged particles, and all of those things get flung out into space towards, well, maybe nothing or maybe us, and maybe causing some problems. So this current cycle, solar cycle 25, is a bit stronger than was predicted, and it's certainly living up to that hype. And so kind of the big thing that you may have heard about was a couple weeks ago, there was a very large spot complex that formed called AR, which I believe stands for active region, although I did not look that up, 3664, which is this grouping of sunspots right there. It's about 15 Earths across, and it's one of the biggest sunspot complexes that we've seen in recent history. Actually, well, it's too late, it's rotated out of view, but if you still have your eclipse glasses, you could have put them on and taken a look at the sun and actually seen those spots. Don't do that without glasses, please. So with this active region, the sun got a little crazy. There were a lot of very strong flares and coronal mass ejections, which caused some very severe space weather conditions. So this included multiple X-class flares, which are the strongest class of flares that the sun can produce. And led NOAA to issue a G4 geomagnetic storm warning for the first time in almost 20 years. Now, yes, this was a couple weeks ago, but there's no sign of stoppage. That weather was certainly kind of once in a generation, but things are still going off. So even though this sunspot complex has rotated out of view from the Earth, it is still flaring, it is still ejecting mass, and there are other sunspots that are forming and doing the same. And kind of keep in mind that we are only at the start of solar maximum. The peak should be sometime next year. So we still have a couple more years where you'll want to stay tuned to your local space weather channel for any big alerts.
And so because there was this big sunstorm, you might have seen the sky change color. I didn't expect to be writing about two major local astronomical events 2 months in a row. We here at Space Drives repeatedly bashed you over the head with the knowledge that a total solar eclipse was coming America's way in April. You could not have forgotten it, but we would have been fools to ever even offer you a hint of being able to see the Aurora Borealis here in Tucson. Usually one must travel far, wide, and north to see the northern lights. And in fact, I was in Iceland last month, the place where to see the northern lights. And what did I see? Clouds. Nothing. But then I was visiting my family in New Jersey for my grandpa's 90th birthday. Happy birthday, Grandpa. And suddenly came the prospect of seeing the Northern Lights in New Jersey. Yeah, right, okay. Light pollution and what else? Also clouds rule the day along the entire northeast corridor, so I didn't see anything at all. But my fiance's family did see it in Ohio, so that's Ohio on the left, and Tucson over here on the right. So you can imagine my FOMO as the pictures started rolling in on Twitter, Slack, text, anywhere in the virtual universe that I was not. The auroras were seen in the Dakotas, Pennsylvania, Alabama, and even Tucson, Arizona. So this was taken by one of our research scientists here on the right at Steward. And absolutely incredible views for 2 nights straight, and 2 nights straight of clouds along the entire East Coast. So you might be wondering what produces all these gorgeous colors. So in short, the magnetic field from the solar storm interacts with particles in the Earth's ionosphere, causing different atomic transitions to emit light at different wavelengths. So this depends on the altitude in the Earth as well as your latitude and the intensity of the sun's incident radiation. So above 150 miles, there is a low concentration of atomic oxygen in the ionosphere, and this causes a pink glow. At higher concentrations of oxygen, which happens at lower altitudes, around 100 miles, the atomic oxygen actually emits light at green wavelengths. And at 60 miles altitude, ionized molecular nitrogen produces purple and blue light. So red, blue, and purple are all associated with extremely intense solar activity, whereas the northern lights tend to be more green in periods of calmer activity in more typical conditions up north. And very intense solar activity is also linked to power outages, as the magnetic fields can damage the power grids. This has happened repeatedly historically. I don't have time to tell you about all the fascinating times this happened in Canada, who deserved it. I didn't say that, but anyway, I don't know, maybe they did deserve it. It's Canada. Anyway, in this particular storm, outages were seen in Scandinavia. Maybe they did not deserve it. Poor Sweden. Anyway, this is a once-in-a-decades event, so sorry if you missed it. The end.
What's your problem with Canada?
I don't know. It's not just Canada, it was Quebec, so now you understand.
Do I? Well, whatever. I'm now 0 for 2, no eclipse and no aurora, so maybe one day I'll actually see something cool about astronomy. No, that's a joke. Okay, so if we start out, as one of the great philosophers of modern times, Shrek always says, better out than in. And you might be surprised that astronomers are pretty excited to have found a planet that might be following his sage advice. So what do I mean by this burping planet? So what we are looking at is a planet called 55 Cancri E, which is a planet orbiting a star about 40 light years away, a sun-like star, that is between the size of Earth and Neptune, but given its mass, we know that it is likely terrestrial. So it is more similar in composition to the Earth, so something maybe rocky, than something like Neptune, which has a thick gaseous envelope. And so this planet, there has been some, I don't want to say controversy, but it's certainly been contested over time. It was discovered, and then for a while its orbital period was hotly debated before it was finally settled that it orbits its host star in just 18 hours. So it's very, very close to its sun-like star. And so this means that it's very, very hot, and it's also tidally locked. So similar to how the moon orbits the Earth, the time it takes for this planet to rotate is the same that it takes to go around. So there's one side of the planet always facing its host star, very close in, so it's very, very hot, meaning that its surface is not rocky necessarily, it's a different kind of rock, it's molten rock. It's probably a lava world. So there's also been some studies trying to find an atmosphere around this planet, but until now, they've been either contradictory or have produced negative results. That is until now. So as has been kind of a common occurrence with astronomy in the news over the last couple of years, JWST comes to the rescue. And so there was a team led out of JPL that has actually found evidence for a fairly significant atmosphere around this extremely hot lava planet. So how did they find it? Normally when we talk, or when I tell you about planetary atmospheres, we find it by looking when a planet passes in front of its star. Light from the star passes through its atmosphere and you can detect the atmosphere. So this is actually the opposite. That's called transit spectroscopy. Here they did something called eclipse spectroscopy, where they actually waited for the planet to go behind its host star, and you can actually look to see the difference in the amount of light you see because the planet is missing. The planet is so hot, it actually contributes to the amount of light you see when you can actually see it, when it's on the side of the star. And so that's here, this kind of line on this plot. If there was no atmosphere, there would have been this top line, but they actually see that the planet is cooler than they would expect, which means that it has an atmosphere that's recirculating heat, and they also see signs of carbon dioxide or carbon monoxide. So this is quite remarkable. For a planet that is this close to its host star and this hot, we didn't even think that it necessarily could have an atmosphere. And if it did, they thought that maybe it would be a very thin layer of vaporized rock, but it is not. And when I say burping planet, it's because it wouldn't be able to hold on to this atmosphere for long, so it's being replenished by outgassing from its interior. And so this is really cool because, well, one, this would be, if real, the first atmosphere around a terrestrial planet that's ever been detected. And this kind of outgassing of an atmosphere is how you, start maybe in a habitable atmosphere like our own planets. Now, this is not in any way habitable, but even still, it's, shedding light on how you might get to an atmosphere like the Earth's early atmosphere that was conducive to the start of life.
What kind of name is Cancri? Usually it's a string of numbers, but I think I like that better than Cancri.
It must be a constellation.
Okay.
Cancer.
It's Cancer. Cool. That's nice. Let's go very far away, past the constellations. It would not be news with Whataburger Jr., that's me, if I didn't open with, it wouldn't be news with Whataburger Jr. without going very, very far away to the smallest possible thing we could see with the James Webb Space Telescope. I'm here, I'm back, and here is another black hole. We are celebrating the discovery of, in fancy terms, an offset AGN, or an offset active galactic nucleus, but in layman's terms, this is just the merging of two galaxies that each have black holes. So when a black hole is accreting stuff, it's active, it's in the middle, so it's the nucleus, the middle of a galaxy, you get it, active galactic nucleus, offset AGN, it's not in the middle. And of course, it's all happening only 750 million years after the Big Bang. We've set another record. So in a publication in the monthly notices of the Royal Astronomical Society, a prestigious journal in the UK known for affordable publishing fees and the irritating requirement to spell ionize with an S, Hannah Ubler and colleagues detailed their discovery of a peculiar galaxy at a redshift of 7.2. In it, they find evidence for a black hole, as traced by broadened hydrogen emission. Boom, done. That makes sense to you, right? A broad hydrogen line is a smoking gun for an accreting black hole. So your paper is basically written for you. All done. But wait, there's more. They used JWST's near-spec IFU, or the Integral Field Unit Spectrograph. That means that you get many spectra across many different physical locations of the galaxy. So usually when I show you a spectrum, that's a spectrum, but that's the whole thing. Usually you get a spectrum of just a little point of light, but for something with an IFU, you can actually map out the whole galaxy instead of just treating this galaxy as one little point of light, which Danny, our nearby expert, so lovingly respects. Okay, so in the IFU data, they find something curious. The broad hydrogen signature, indicative of 50 million solar mass black hole, is actually offset by 620 parsecs from the center of the galaxy. So it's not an active galactic nucleus. they find instead in the center of the galaxy a different spectral signature of a black hole. It cannot be coming from the same location in the galaxy. So this means there's evidence for a second supermassive black hole, which is likely a consequence of the fact that there were two galaxies, and you can almost see, if you look at the red thing on the right, you can see that it looks like there are two nuclei for this galaxy. As a consequence, they have brought their black holes along for the ride, and they are crashing into each other. So a curious thing that has caused many astronomers to bang their heads against walls and continue to get money from the government is to ask, how did black holes form? You too can ask this question, how did black holes form? They form too fast. They get too big too fast. So when we're talking about these very high redshifts, only a few 100 million years after the Big Bang, there's simply not enough time for it to accrete enough matter. And so one thing that people have come up with is that you have merging black holes. But this seems like a very unlikely thing. Space is pretty empty. It's hard to find black holes that are currently accreting mass. And so actually seeing merging black holes is not like a reasonable thing to be looking for in surveys, but here it is. There are two signatures of two different black holes, and so this is kind of lending credence to that theory that black holes grow so quickly because they're crashing into each other. So that's fun, and definitely will not keep you up at night. So that's that on astronomy in the news. Thank you so much for listening. Taking off my silly hat now, back into my very serious hat as your MC. We have a second talk now, and it's coming very soon. Pretend like you're not seeing behind the scenes. I could do a dance, maybe. I'm not going to do a dance. I could continue roasting Canada for the next 30 seconds. Sorry, I have no beef with Canada. I just made this up. Okay, so thanks for listening to me talk. I'm done talking. I'll be back in 20 minutes when Arin's done. Thanks.
Can you guys hear me well? Cool. So yeah, I'm Arin. I'm a second-year PhD student here, and I'll be talking about worlds colliding. So before I get into that, I want to give a quick overview on how stars and planets form. So basically, we have here the famous pillars of creation. These are what we call stellar nurseries. So stars are being actively formed here. Something like some supernovae, stars exploding will set off will destabilize these clouds that will then collapse to form the stars and planets that we know today. And so this is a James Webb image, actually. Is this the pointer?
Yeah.
There we go. And so these red dots that you're seeing here, they don't show up too well, but they're actually signs of stars ejecting the gas that they're actually accreting. So this happens out of their poles, and so you can see that this is active star formation going on here. And so if we actually move where we zoom in on one of these, you actually get something like this, another fantastic JWST image. This is a protostar or a baby star. It's only 100,000 years old, so compare that to the 4.5 billion years of our solar system. It's very young, and this is also ejecting the gas around it vertically here. So this hourglass shape you're seeing here is due to the star that's still forming. It's not fusing hydrogen in its core yet, ejecting these. And so if you actually zoom in on here, you can actually get the disk itself, and this is where the star is, and this is where planet formation is occurring. And the reason why it's dark and kind of there's this black line here is because that it's actually obscured by all the dust that's in front of it. And so if we zoom in and evolve this a little further, we get a more evolved protoplanetary disk, or a disk where planet formation is actively ongoing. That should say a million years, apologies there. So this occurs also when the star is really young. And so the star in the middle is actually accreting gas and dust onto it, while these planets, or what's thought to be planets, are carving out these gaps here. And then finally you're in the debris disk stage. So this is kind of unsure where the debris disk stage ends, but it's about 10 million years to about 1 billion years old. And so this black region that you're seeing here is actually just what we use to block out the starlight, so we can see the dimmer dust around it. This white stuff is just a data processing noise, and then this ring itself is made of secondary dust, and I'll get to what that means in a second. And then once this is over, after about 1 billion years, we have an evolved solar system, or a mature solar system, just like our own. But in this talk, we'll be talking mostly about debris disks and how they form. And so there's two ways that these form. The first is thought to be, after planet formation ceases, you have all of these comets and asteroids, which I'll call planetesimals going forward. And if you have the presence of a giant planet, what happens is that it will affect or will change the orbit of these planetesimals. And as you change the orbit, you can get them to collide. And this collision creates fine dust, which is then what we see in images like this here. However, there's a second thing that I think is not spoken about enough, but I think it should be considered. And the second is if you piss off the Empire. So if you piss off Emperor Palpatine, he will come and blow your planet up, arguably creating lots of fine dust, which could create a debris disk. The jury's still out. But jokes aside, I'll be talking about two really well-known systems here. Beta Pictoris, which I'll be calling Beta Pig, and then Fomalhaut. So Beta Pig is about 60 light years away from us. It's 70% more massive than our sun. It's very young at only 20 million years old, and it has two known planets, Beta Pig B and C. Beta Pig C is at about 3 AU, or astronomical units. For reference, that's 1 AU is the distance from the Earth to the sun. So 3 AU makes it at about where our asteroid belt is in our solar system. It's 10 times the mass of Jupiter, so it's very, very massive, and it's about 50% bigger. So very huge, and we have nothing really like it in our own solar system. And Beta Pig B, about the same mass, about 10 times the mass of the mass of Jupiter. It's about 50% bigger, and it's located about 10 AU. So that's actually exactly where Saturn is in our solar system. And so for actually some Tucson trivia, Beta Pig B, the disk was first imaged here in Tucson at the Lunar and Planetary Lab. And so this was the first time that circumstellar dust had actually ever been imaged around a star directly. There's some controversy behind it. Apparently a grad student who built the chronograph, which is used to block out the central starlight, was not given the credit they deserved. So if you're here, I'm sorry. But yeah, I think it's quite amazing. And if you look at the scale bar here, actually, that says 500 AU. So this stretches 500 AU in each direction. And for reference, the farthest planet in our solar system, Neptune, is only at 30 AU, so this thing is very extended. And there's a movie that should play. Yeah. And so this is Beta Pig B. This is actually a movie of it. It was one of the first planets to ever be directly imaged, and you can actually see it over time complete its orbit around its host star. So what it's doing is it's moving behind this chronographic mask, which is used to block the central starlight. And yeah, and this is one of the only directly imaged planets that we can see complete a whole orbit. And so I think that's quite amazing. And so this planet being there and orbiting means that we can actually see it affect the disk, hopefully.
Let's see. Is it gonna go there? So
change the slide.
There
we go. So how does this disk look with technology not from the 80s? If we use the Hubble Space Telescope, which uses optical light or visible light that we can see, you can actually see that this disk is asymmetric. And so imagine a disk that's circular, and then you've rotated 90 degrees, and then, so you're seeing it kind of from the edge on case here. So you can see that the right side is actually brighter than the left side, which at first is a little perplexing, because if this is just dust that's orbiting a star, then both sides should be approximately the same brightness. So the fact that it's not that raises some questions as to what could be going on in this case. And so observing things at different wavelengths allows us to peer into more parameters and see what's actually going on. So if we look at the thermal infrared taken with the Very Large Telescope in Chile, you kind of see the same thing. You see that this right side is brighter than the left side. Okay, but this is all dust, right? So what if we look at the gas? There's some gas in the disk. What if we look at that at radio wavelengths using the Atacama Large Millimeter Array, also in Chile? You see the same thing. In carbon monoxide, the right side is brighter. There's more carbon monoxide on this side compared to the other. And so there's a lot of hypotheses that were thrown out as to why that could be the case. There could be a giant collision that happened with like some Mars-sized planets or planetesimals, or you could have an unseen planet out here that's trapping this gas and dust over time, but we don't really know. So then James Webb came along, thankfully, and this is also in the thermal infrared, but this gives us a much better sensitivity, so we can see more features here. And so we found that in this image you can see that there's a collision that occurred about 150 years ago that is actually located around the same region, and so this region here. that we saw these clumps at. We don't know if those clumps are the same reason, are due to this collision, but you can see the signature of it. Do you guys want to say what you think the collision feature is? No? So it's this thing right here. So yeah, and then there's a colloquial name that was given by the authors of this paper for some sort of animal, part of an animal that it looked like. You guys have any idea what it might be? Swan's one of them. So it's a cat's tail. I know it curves the wrong way, but you get the point. And so it's thought that something that's the size of, so two objects the size of some of the smaller moons of Saturn or Jupiter are actually responsible for this. So these objects collided 150 years ago, and the dust was then ejected from the system, causing this cat's tail. And I know what you're thinking, but they might be closer than we think, but it's okay. And so for reference, this is Mimas next to the Earth and the Moon. I know it looks small, but if that thing hit the Earth, we'd all die. So these collisions should not be taken lightly. Next, I'll be moving on to Fomalhaut. Fomalhaut is about 440 million years old. It is located about 20-ish light years away from us, and it's actually a triple star system. So you can see one of its companions here and the other right there, but we'll be focusing on the main star for this case. So here is Fomalhaut. I actually cheated a little bit. I showed you the image earlier, one of the images. So again, this blocks out the starlight. This is all data processing noise. But then here's the disk itself, or the debris ring, to be more correct. There's also a collision here, but this one's a little harder to see. You guys have any idea where it might be? I also made this image a little blurry to make it harder. But it's located right here. It's this tiny point. And you might be wondering, why do they call it Fomalhaut B planet here? So when this was first discovered in the early 2000s, it was thought that this could be most likely due to a planet that's actually orbiting the Fomalhaut star. What happened was that subsequent follow-up imaging found that this point source was expanding and also getting dimmer, and then it eventually faded from view, so we don't see it in current imaging. And so that's when the hypothesis that this is actually maybe two asteroids colliding, and we're seeing the dust that's created from it expanding came about. And the person that actually made the Beta Pic B movie, made a really cool movie of this dust cloud expanding and moving with time. And so, yep, right here, so you can see it get brighter and moving. And yeah, today we can't see it anymore. Perfect. Yeah, so just to kind of reiterate, it's thought that some of the largest asteroids in our solar system, the equivalent of that in the Fomalhaut system, collided, creating what we see today. And so I just want to bring your attention also to how much technology is actually, how far it's come. So this is the Hubble Space Telescope image. Again, this is what we have to block out of the light from the star. This is all data processing noise, and then we have this ring itself. But when we actually peered at this with the James Webb, we find this. And so all of this area that was contaminated by all this noise turned out to be an area that's full of actual dust. And there's actually some rings here, there's some gaps here that actually might be due to planets carving them out. And this was all done here at the University of Arizona, so which I think is amazing. So James Webb is really revolutionizing our understanding of these debris disks, and I think will continue to do so for the years to come. And I kind of wanted to finish with our solar system as a debris disk. So when our solar system was at this stage, what was going on here? And so the most important thing, in my opinion, is actually the collision that formed our moon. It's thought a protoplanet the mass of Mars, or the size of Mars, came in and slammed into the Earth, ejecting a large piece of rock, which then coalesced into our moon. And so the reason why this is so amazing is because a rocky planet like Earth having a moon as large as it does is not normal, and it should not form in any other way other than this. And so the moon also has had a huge effect on life on Earth by stabilizing the axis on which Earth rotates, and then it's responsible for the tides, and it absorbs asteroid collisions, so because the moon's so cratered. So it really has had a large effect on life on Earth, and probably is one of the reasons why we're here today. So I think that's amazing. This is a real supercomputer simulation that they did at NASA. If you could go to the next slide. Oh. There we go. And yeah, so this is just an image of the Earth kind of transiting in front of the moon, just so you can get an idea of really how large it is. And this is also why, like, Venus doesn't have a moon, Mercury doesn't have a moon, and the 2 moons of Mars are just tiny little asteroids. And so I actually stumbled upon this. I kind of want to end here. I stumbled upon this while I was actually doing research for this talk. So it's thought that about 500 million years ago, 2 asteroids in our own solar system collided and created, like I said, large amounts of fine dust, which then actually went on to envelop the Earth's upper atmosphere over time, lowering the amount of starlight that actually hits the surface and causing the Earth to freeze over. So if you think that this might seem a little distant and removed, but it's really can have large impacts on life as we know it on Earth. And I kind of just want to end on this note. Don't mess with the Empire or they will turn your planet into a debris disk. Thank you.
Thank you very much for that. We have plenty of time for questions. What are your burning questions? Just repeat the question. Surely someone has a question. Yes. Either any of them. Speak. Whoa.
All of them. So the question is, how much time is wasted allocating observations towards galaxies instead of disks? And the answer is all of them. Unfortunately. Sorry, galaxy people. What? How do we know our data isn't just noise? Because it's very unlikely that it's noise. So is the question how long the remnant would last after collision? So it actually depends on the wavelength that you're looking at. So what happens is that if you look at the optical light, you're probing really, really small grains, so less than, on the order of the wavelength of visible light. And so those are actually susceptible to radiation pressure, so the pressure of photons actually bouncing off the particles and they get ejected out of the system, and so that honestly only really lasts maybe 10-ish years. However, if you go to longer wavelengths where you probe bigger pieces of dust, that can last way longer. So that picture of Beta Pig, they think that collision occurred 150 years ago. So it really depends how you're looking at it, what wavelength of light you're looking at. So you're asking if the small pieces that were ejected from that simulation that formed the moon, if we can see them today, or if we can find them today? Yes. So whether a certain asteroid is due to that remnant or from the initial formation of the solar system, I'm actually not sure. I think one way that you could understand that is looking at it spectroscopically. So looking at how much light it reflects as a function of wavelength that you look at it. That's unfortunately not my area of expertise, so I could not tell you for sure, but my email was there, so if you want to email me, I could definitely look into it and get back to you. Yep. So yeah, the question was, are these debris disks analogous to our asteroid and Kuiper belts? And the answer is yes. They definitely are. Would you be able to observe it if you were looking at our solar system from a different star? Probably not, because collisions between them are so infrequent, and the collisions are what create this fine dust that which you can then observe. So they're definitely analogous. They're yeah, they essentially are. But you would need a very sensitive telescope to be able to actually see it, and that's why you can see them at younger ages, because you have more asteroids and comets that can then collide to create dust, and then as those diminish with time, it becomes more unlikely that you'll be able to see them essentially. So that's a great question. So the question was, if the Empire destroyed a planet in a solar system or in a planetary system, how long would you be able to see the debris disk for? So you would basically be able to see it on, I'm not sure the actual number, but what'll happen is that if you create no more dust in that time, the smaller grains will be ejected from the system, and the bigger grains will eventually, through a mechanism called Poynting-Robertson drag, will fall into the star. I think that acts on a time of like at 100,000-ish years to 1,000,000 years, so around then, between that range, I would say.
Okay, thank you very much. Let's thank our speakers one more time. All right, that's a wrap on Space Drafts 98, I think. Do we have a show next month?
I don't know.
I have no idea if there's a show next month. So follow us on Twitter and Facebook and find out if there's a show next month, and you can come back. If there's not a show next month, there will be one someday on a Tuesday, and you can come and hear about astronomy again. Thank you so much for coming. Please tip your bartenders and come check us out at the merch table for like 4 more minutes before I go home. Thank you. Bye.